Hi, everyone. This lesson is to review more logarithms, and let's get started with a warm-up on transformations of an exponential function. So for this problem right here, I would start off with graphing the parent graph, which is y equals 2 to the x power. Of course, I would always start plotting for x and y. I'd plot 0 and 1 as my two base functions or two base coordinates that I want to plot. So in plotting 2 to the 0 power, I'm going to get 1. 2 to the first power is 2. So we start off with 0, 1, and 1, 2. And our graph, I can definitely plot more points, but I do know this is exponential, and it is going to go up like this. It's exponential because of the variable that's in the exponent. I also know that there is a horizontal asymptote because exponential equations, functions do not have vertical asymptotes, and so they do have a horizontal asymptote. Now, this is just the parent graph. We haven't graphed this completely. We need to do a few things. Number one, you want to do your reflections first. This negative sign in front of this value up here tells me that I need to reflect my equation across the y-axis, which is right here. So in doing that, now my graph is going to come across like this and look like this. In addition to that, it's telling me to move my variable move my graph 4 places to the left. So now my graph is going to be 4 units to the left, and so my graph will look like this. Okay. Go through those 2 points. And this value here, -5, tells me that my equation is going to drop down 5 units. My asymptote goes with me. And so it would look something like this. Now, the transformations for this graph, and that's my final graph right here. If this says to list all the transformations, the first transformation would be to reflect across the y-axis. The second transformation would move my graph left 4. And these are, of course, after graphing the parent graph. Reflect across the y-axis, move my graph 4 units to the left, and move my graph down 5 units. And so if you were to be asked, give me 2 points. Well, you're not going to use these points because those are the points for the parent graph. You would need to plug in points here or to keep track of where you moved your graph from 0, 1, and 1, 2. So if I wanted to plug in, let's say 0, now 0 plus 4 is, so I would go like this. Here's x, here's y. I would go 2 to the negative parenthesis, and this is 0 and 1. 2 to the negative parenthesis, 0 plus 4, and then subtract 5. So 2 to the negative 4 power. Well, that's 1 over 2 to the 4th power, which is 1 over 16. Minus 5 is going to give me 1/16 minus 5. I don't know. I'd have to multiply by 16 over 16, get a 5 times 16, 1 minus that, and that's going to give me 0, a graph down here. A point down here. And then likewise, if I want to plug in 1, I would go 1 plus 4 is 5. 2 to the negative 5 power is 1 over 2 to the positive 5 power, which is 1 over 32. And then I would take that number and move and subtract 5. And so that's also going to give me a negative value down here. So you can plot points. I would use my calculator, or I would, just finish these out right here to get actual points. You also can plug in a negative number up here because there's still negative values. So if I said, let's say -4, well, -4 plus 4 is 0. 2 to the 0 power is 1. 1 minus 5 is -4. So at negative, what did I plug in? So if I plugged in -4, you just plug those values in and you'd be able to get additional points if necessary. So let's get back to logarithms. solving an exponential equation, solving this, you can do this two ways. Way number one is to get a common base. And notice that 4 and 8 are not going to be common bases, as is. However, I can break these down to 2's. So 4 can be rewritten as 2 to the second power. But notice that there's already a 2x minus 1, so that stays up there. That doesn't come out, that has to stay there. 8 can be rewritten as 2 to the third power, but again, notice the x there. Well, if the bases are the same, I can set my exponents equal to each other, and now I just have to solve for x. It's a linear equation, so 2x minus 2 equals 3x. I'm going to subtract 2x. I'm going to get x is equal to negative 2. Now, I said that there were two ways to do this, so let me show you the other way that you have a choice of doing this. If you have 4 to the 2x minus 1 is equal to 8 to the x power, what we talked about was in the previous lesson, Logarithms Introduction, was to take these values that are in our exponent out front. And the act of doing that, which is the inverse, changing an equation from an exponential equation to a logarithmic function, that's an inverse. Just like what we were talking about in the previous lesson, if I had, say, x plus 3 equals 10, the act of moving this 3 to the other side, I would take the inverse of positive 3, which is negative 3, okay? And I would subtract that. Well, it's the same concept in that the inverse of an exponential equation is a logarithmic equation. So that's what I'm going to do. So I'm going to go 2x minus 1. That's a quantity, and you cannot break into that yet. And you would say log 4 equals. Now, remember, if you log one side of the equation, you do need to log the other side. So this becomes x log 8. Now, there's a lot going on here. I personally would not distribute. I would try to get this value over here, meaning if I move this to the right, and then the x, if I divide it by x on both sides, I would have 2x minus 1 divided by x is equal to log of 8 divided by log of 4. And so what I just did was I created this a little bit easier to try to solve. Now I do need a calculator in order to solve log of 8 divided by log of 4 if I were using my calculator. So I'm going to go log of 8. I'm going to get approximate that value divided by log of 4. Okay. Oops. Delete. Okay, so what is it? Log of 4 and approximate 1.5. So what I would do then, what I get is 2x minus 1 over x equals 1.5. And actually 1.5 is 3 halves. I'm gonna change that to 3 halves. Okay, and so we have 3 over 2. I'm going to cross multiply. I get 3 times x is equal to 2 times 2x minus 1. And if you notice, this is what I have right here. And so I would just continue that on. So there are two ways to solve this. Of course, this side on the right is a little bit longer, but it still is a way to solve the problem if you choose to log both sides. These ones right here, base to a cross equal sign. So we're going to go 3 to the second power is equal to 4x minus 7. We're going to change that base. Notice now I went from a logarithmic equation to an exponential. And when I convert that, I'm actually finding the inverse. So now I have 9 is equal to 4x minus 7. Add 7, I get 4x equals 16. X is equal to 4. X to the second power, so x to the second power equals 64. Of course, in this problem, it is quadratic. You're not going to get the bases equal to each other. There's a couple of ways to solve this. One way to solve this is to square root both sides, okay? And so then you're going to get x equal to 8. A recap on logarithms. So this is what we did before. Oops, let's move that over. So we're going to go 25 base to cross the equal sign. And so that's going to be 25 to the x power is equal to 5. If you can get the bases the same, then try to do that. Okay, so in order to get the bases the same, I'm going to take 25 and rewrite that as 5 squared to the x power is equal to 5 to the 1 power. Bases are the same. 2x is equal to 1. X is equal to 1/2. For this problem, base to cross equal sign, so 3 to the x power equals 27. 3 to the x power equals 3 to the third power, x equals 3. Now, in the previous lesson, I talked about doing this a different way. So let me show you how you would log that. You would take the x out front, and you would get x log 3 is equal to log 27. And x is equal to log 27 divided by log 3. Now, just so you know, you would need a calculator for that. This is a quantity, and so you would definitely not be able to divide your logs, and also you would definitely not be able to divide these numbers. You can never do that. So these are quantities. You would have to punch those calculators or the values into your calculator. Now, what I do want to show you is that going from here to here, see how it's log base 3? So we started off with log base 3 of 27. This is our change of base formula, and we talked about this in the previous lesson. A lot of people don't need to go through this one step right here because they can go from here to here because that's the actual change of base formula of log base 3 of 27 says that's a log of base 10. See, I said change of base because what I did was I just went from base 3 to base 10. And I know you don't see anything there, but when you don't see something there, you know it's base 10 because that's our number system, base 10, 0 to 9 digits. That's why it's base 10. Anyway, we end up getting x equals 3. For this problem, base to cross equal sign, so 9 to the x power equals 81. Remember, I could always use my change of base formula, and I would actually get log of 81 divided by log of 9. And I would go right to my calculator and type that in. However, I don't need to use my calculator for these problems or this problem particularly because I can get my bases the same. So I can say 9 to the x power is equal to 9 squared. So for this problem, x equals 2. And doing this again, I would of course get 2. But please keep in mind that this is just one way of solving the problem because again, 9 can be rewritten as 3 squared to the x power. And 81 is actually 3 to the 4th power. Bases are the same. I get 2x equals 4, so x is equal to 2. So just another way of doing this, instead of going 9 squared, you can do, there are several ways to do this. 2 to the x power, so 2 to the x power equals 1 over 32. Well, 1 over 32 is the same as saying 2 to the x power equals 1 over 2 to the 5th power. 5th power, and some people are, where did you get that from? What I did was I just factored this out, 4 times 4, and then 2 times 2, 2 times 2, so that's 5 2's. Anyway, you need to bring this to the top, so you have 2 to the x power equals 2 to the negative 5 power, so x equals negative 5 for that problem, okay? That one is here. The next problem, base to cross equal sign, so you'd say 5 to the 3rd power equals x. This one I don't have to log, I don't have to get the same bases because this is just saying x is equal to whatever 5 times 5 times 5 is, and that's going to be 125. So that would be my final answer, and that one's pretty simple. This is 3 squared, so base to cross equal sign equals x. So in this problem, x equals 9. So yeah, you have a lot of different ways, of course, to solve these problems. A lot of choices. Logarithms are fun. This one just says write in exponential form. So we're going to go base to cross equal sign. So q to the r power equals 24. Now, they're not asking me to solve this. They're not asking me to log it. They're not asking me to do any of that. They just said rewrite it in exponential form. So in doing that, this is my answer, and I'm done. That's a 24. This one says to write in log form. So I would say that's log base 2 of 7.621 equals C. And if you wanted to check that, you would go to the C power base to across the equal sign. And that's what they're asking me. They didn't ask me to solve it. And of course, if you had the TI Inspire CAS C8S calculator, you could just type this in your calculator because the TI Inspire will do a change of base. And so most calculators like the TI-84, well, actually, I'm going to take that back. You could do that on that. You just have to go to the catalog, but you could do a different base in logarithms. On the TI-84, you just actually would need to go to the catalog. These problems right here doesn't have a variable, so I'm going to put one here. I'm going to go 6 to the x power is equal to 36. I'm going to get the bases the same, so I'm going to have 6 to the x power equals 6 squared. So in this problem, you have x is equal to 2. For this problem, again, base to across the equal sign, so you have 5 to the third power equals x. We just did this problem, so that's 125. This problem, we're going to say there's no variable there, so we have 2 to the x power equals 1 over 32, which is 2 to the 5th. Does this look familiar? 2 to the x power equals 2 to the negative 5 power, so x equals negative 5. 25 to the x power, so base to across the equal sign, is equal to 5. Let's get the bases the same. So we have 5 squared, so this will be 5 to the second power. Don't forget the x, this x, that's already there. Even though you're replacing 25 with 5 squared, you still have the x there. So that equals 5 to the 1 power. Bases are the same, 2x equals 1, x equals 1/2. For this problem, remember in the last video, we talked about if my bases here are the same, my answer is 25. And in this problem here, you have the bases. E to the ln power is just 1. 1 times 10 is 10. So I'd like to start off doing just a logarithm. And so I like Desmos. Desmos is good. Desmos you can't use on the you can't use Desmos. It's an app on your calculator, and an app on your either phone or your computer. So you'd go to Desmos graphing. And if you just went in and typed in log of x, what you would get if you plug that in is basically a graph that looks like this. Okay, and so what that is your logarithm. And notice that this is base 10, so it's 10 to the y power is equal to x. Well, in doing this by hand instead of with a calculator, because sometimes on your tests and whatnot, you can't use calculators. So I just rewrote that. That's not the inverse, right? That's what the logarithm is. And if I were to graph this, what I would do is x and y, I would actually plug in points for y because see, y is my exponent. So if I plugged in 0 for y, 10 to the 0 power is 1. And if I plugged in 1, 10 to the 1 power is 10. So my points here would be 1, 0, which is here, and 10, 1, which is here. And so that's my graph of log base 10 of x. In order to find the inverse function for this graph, I would remember, you can always find the inverse by reflecting your graph across the y equals x axis. And so instead of this being 1, 0, the inverse would be 0, 1. And the inverse of 10, 1 is 1, 10. And remember, if this is actually exponential, you do have a horizontal asymptote for this. But this graph here is logarithmic. And for log equations, okay, for logarithmic equations, you have vertical asymptotes. And so that gave you a vertical asymptote here at x is equal to 0. But the inverse, which is a exponential function, remember, an exponential function, they have horizontal asymptotes, and those start off at y equals 0 before I actually do any kinds of transformations. So see log base 10 of x, so 10 to the x power, 10 to, in this case 10 to the y power equals 10 to the y power equals x. And for this graph, I plugged in my 2 points. And again, I don't know, you really can't say this enough. If your variable is y up here, you're going to plug in x, y, you're going to plug in values for y. If your value has an x in the exponential part, then when you plug in points, you're going to plug in values to x. So whatever variable is up on top, that's what you're going to plug your values in to solve. These are inverses of each other, so you can even put them on the same graph and reflect them across the y equals x axis. So again, we're talking about inverses. So if you were to go to Desmos in your graphing calculator application, either on your computer or on your cell phone, I would like you to pause and type that in, y equals ln of x. And then once you're looking at that, try to find, what are my asymptotes? What's the domain and range? That kind of thing. And look at the graph, because some of your graphs do, like in the previous slide, we have vertical asymptotes, and then we have horizontal asymptotes. Exponential equations have horizontal asymptotes, and they start off right here at y equals 0. But this being a logarithmic equation, you have an asymptote that starts here at x equals 0 before you do any kinds of transformations. Likewise, if you just graphed y equals ln of x in Desmos or on your graphing calculator, what you saw was that you have, remember, ln of x is the inverse of e to the x power. And e, this is the point 1 comma e is the same as 1 comma 2.718. And so these are inverses of each other. 0, 1, inverse, 1, 0. 1 comma e, inverse, e comma 1. And so just know, again, exponential equations, this is exponential. And the reason you can tell that that's exponential is because your variable is your exponent. So when your variable is your exponent, it's exponential. And that means that you have an asymptote that goes across right here at y equals 0. And for your domain, for this problem, your domain would be negative infinity to infinity, and your range goes bottom up. Where a domain goes left to right, your range goes low to high. So in this case, not including 0, so you can't include 0, so that's why it's a parenthesis, and then that's going to go to infinity. For this problem here, my domain, and remember I have a vertical asymptote. For any kind of logarithmic equations, I have a vertical asymptote, and that vertical asymptote is at x equals 0, whereas for exponential equations, I have horizontal asymptotes. So, what? Domain, wrote it. My domain goes left to right, so not including 0, because 0 is an asymptote. It's going to go from 0 to infinity, where my range is going to go low to high, which is negative infinity to infinity. Now, just a couple of things that I want to talk about right here on this slide, and that is, remember when we were talking about inverses in the previous video lessons? When we were talking about inverses and you were to graph, if you had, let's say, y equals 2x, plus 7, and I were to take the inverse of that, remember I would flip my x and my y, so I'd have x equals 2y plus 7, and then I would solve for y, so I'd get 2y is equal to x minus 7, y is equal to x minus 7 divided by 2, and then that's my inverse. Well, the domain and range for this equation is going to flip and be my domain and range for that equation. So they are, my domain for my first equation is my range for my inverse equation. You see how they're the same? They're the same. Likewise, my range for my first equation is my domain for my inverse equation. Okay? All right, so let's just go back and talk about some transformations for graphs. This value here in front is my vertical stretch or shrink. This value, and these are just for true for my natural logs. This value here in front that's going to be plus or minus. That's your log. I believe that's your base 10. X plus or minus. Oh, that just is your that. Oops, hold on a second. These are off a little bit. That there is my horizontal shrink. That's my B. And this one moves it right or left. And this one moves it up or down. There we go. So my horizontal stretch or shrink is this B value in front. Also, keep in mind that this might reflect across my y-axis, whereas, depending on what that graph is, if it's negative. This moves my graph left or right. This moves it up or down. Always, and a lot of people will take a log equation, and one of the steps to doing that is to convert the log to an exponential expression, because let's say you don't have a calculator that you can use on a test. If you don't have a calculator, then what's going to happen is, how do you graph a base 5 equation? Well, if I had, let's say, y is equal to log base 5 of x, how am I supposed to graph that? I would change that, and I would make it I would go base to across the equal sign. I would go 5 to the y power equals x, and I would plot points that way, because now I went from a log to an exponential, and that's a little bit easier when you're trying to graph. So let's start with a natural log. Okay, so you can do this a couple of ways. The first way, if you actually change this to ln to e to the x power, okay, that's your parent function. Y equals ln of x, you would start there. It's asking you, see the negative sign right here, to reflect it across in the front. You're going to reflect it across the x-axis, and this right here is saying add to. So there's just a couple of different steps. The first thing we did here was, if I were to change ln of x to e to the x power, that's your e to the x power right here. Okay, and then this negative sign, because you do the reflections first, that's asking you to reflect it across the x-axis, and so that actually would be something like this. That's right. And then you would graph it, and then reflect across the y-axis. But then what happens is then you would move it up too. But keep in mind, this is a reflection itself. That's a reflection across y equals x, which is this right here. So when you don't have to do it this way, you can graph ln of x, so you know that if that's, so think of it like this. If I chose not to graph this, let's eliminate that. Let me eliminate this for 1 second. If I chose not to graph it that way, I think sometimes it's just easier to graph it like this. If you had ln of x, well, think about what ln of x is. Ln, if that is the reciprocal, or the, the inverse of e to the x power. Remember what e to the x was? That was 0, 1. So what's the inverse of 0, 1? So the inverse of 0, 1 is 1, 0. So there's 1, 0. And then if for e to the x power, you had another point, if you plugged in 1, you would get 2.718, like that. Well, the inverse of that is going to be 2.7181. And so what that's doing is that's showing me, reminding me that my graph is doing this. That's how I would start with that graph. Now, the next thing that I would do after I started, and this is the parent graph of just ln of x. Then I would take my reflection, negative. Remember, this is different than, what I did before. The next thing I would do is I would reflect it across the x-axis. And in doing so, now my graph looks like this, okay? The third thing I would do is add 2. And so all that does is it takes this graph right here and it moves it up 2, okay? So, and then you get this as your final graph. But like I said, there's a couple of different ways to solve this, and you have to do graph it whichever way is more comfortable for you, but also a way that will give you points, because you will need to be marking points on your graph. A couple of things for here, listing the steps. You could graph a log equation. Now remember, a log equation is an inverse of 10 to the x power. Well, think about it like this. Well, 10 to the x power, if I were to plug in 2 points, my 2 points for that, for x and y, for 0 and 1, would be 1 and 10, right? So if a logarithm is the inverse of my exponential graph, instead of it being 0, 1, the inverse of 0, 1 is 1, 0. So there's that point. And then the inverse of this graph, of this point, 1, 10, is going to be 10, 1. And remember, logarithmic graphs have a vertical asymptote, and it starts at x equals 0. Okay. Well, so far, my graph for my I missed it. Sorry about that. So far, my graph for this, let's try to get that. Okay, let's just delete that. Let me try again, try to graph this a little better. Going up like this. There we go. Okay, now this negative sign in front reflects it across the x-axis. So it's now, instead of it going like that, is going to go like that. And this point here is going to be 10, negative 1. And this point is still the same. And this graph, right, this value here takes my graph and moves it negative 1. So that means not only is my graph moving, but so is my asymptote, because my graph just gets closer to the asymptote, but can't ever touch it. Now this problem here, this problem here has a few more steps. And what I want you to notice is that this is a base 2, all right? You don't know how to graph a base 2. I mean, you could graph it like this, to the x power equals y, and then you would find the inverse of that. So you'd graph the inverse, and then of course flip your final value over the y-axis. Or you can graph 2 to the y power equals x, and then plot points for y. So remember, if your y is your exponent, then you're going to plot points for that. So 0 and 1. So if I plug in 0 for y, 2 to the 0 power is 1. If I plug in 1 for y, I get 2. So this isn't an inverse. This is just this graph of a log base 2 graph. So we have 1, 0, and then we have 2, 1. So, and then remember, you have a asymptote. That's a vertical asymptote. So my graph goes like this, like that. Now, to the right 3. So this is going to take my graph and move it to the right 3. And of course, you're going to move points with you. So right 3 and then up 2. So, I would plot points as I was moving my graph over, etc. I'm not going to do that right now, but you should verify that. And then, of course, go to your graphing calculator or to Desmos and verify those, that your graph is accurate. You need to practice these, and you need to practice. So this one is asking me to graph the function using transformations. Now, keep in mind, e to the x power, y equals e to the x power, is actually y equals 2.718 to the x power. Well, we just finished graphing y equals 2 to the x power, right? Which went through 0, 1 and 2, 1, which looks like this, right? Well, this is the same graph. The only difference is it still goes through 0, 1, but it's just a little steeper because it's 2.7 instead of 2. So you would start off with that graph. Then you would do your reflection. okay, that's going to reflect across the x-axis. So this now is going to, that's not the x-axis. And then it's going to look like this, and it's going to go down. This value here is going to move my graph to the right. So here are my steps. Start off with y equals y equals e to the x power. Notice the points. You have 1e and 0, 1. Then you're going to reflect it across the x-axis. And now I have 0, -1, and 1, -e. Remember, we talked about this before. The reflection across the x-axis changes that value here on the right. And lastly, this -3, x -3, moves my graph to the right, 3. And so that just takes this whole value, and instead of it being 0, -1, now it's 3, -1, because I moved to the right 3 points. So it's really important that you keep the points and you follow the points as you move. Okay. Now this is not a graphing problem. This is a solving problem. So we have e to the 2x is equal to 5. Now, there's a couple ways to solve this. Number one, if you have e to the 2x, remember, you can make that in the act of moving this right here out to the front is taking the inverse. Well, what's the inverse of e to the x power? It's ln of x. So you have 2x ln of e is equal to ln of 5. Well, this right here is 1. So I really have 2x equals ln of 5. Well, divide by 2, I get x equals ln of 5. And, ln of 5 divided by 2. And I would actually need to use my calculator for that. And I have that value right here, which is 0.805. So this is just how I would solve this. This here just goes from e to the 2x power to 2x. And the reason they did that is because most people know that ln of e is 1. I just like to write out all the steps, but that's where that went. Where did the ln of e go? Well, ln of e, maybe in your notes somewhere you could write that down, that's equal to 1. And I could explain that a little bit even better than just saying that. And I could say, well, remember what ln represents. Ln is the same thing as saying log base e of e. Well, log base, see, remember when these are the same value? Okay, that's 1. And so that's 1. That's where it went. And so that concludes more logarithms. I hope that helped you, and I'll see you next time. Thanks.